We're going to learn how to specify coordinates and directions and planes in cubic unit cells. First, let's have a look at a typical generic unit cell. We know that what we can do now is specify three axes that run along each edge of the unit cell. Notice that the axes do not have to be at right angles. Each axis will have a unit associated with it, a vector that is the size of the lattice parameter in each direction. So if I go one step in the x direction, that will mean traversing distance equal to one lattice parameter in the x direction. If I go one step in the y direction, that means I will move over, I will make a displacement of equal to the size of the lattice parameter in the y direction, in this case labeled b. Similarly, in the z direction, I will, if I make one step in that direction, I will be moving in the z direction by a quantity equal to the length of the c-axis. So we can use this as a coordinate system, and where the unit of each displacement is equal to the lattice parameter. This is applied to determine coordinates in a cubic unit cell. If we put our origin here, this is the 0, 0, 0 location. This edge of the unit cell is the 1, 0, 0. The 1 represents that we have traversed one lattice parameter. This location requires us to go one step in the x direction and one lattice parameter in the y direction. Hence, the coordinate is 1, 1, 0. This top corner here represents a displacement of one step in the x direction, one lattice parameter in the y direction, and one lattice parameter in the z direction. Hence, the coordinate of that position is 1, 1, 1. Having defined coordinates, we can now calculate directions. We're going to calculate what are known as the Miller indices of direction C using this four-step process. First, we're going to determine the coordinates of the 2 points that lie on the direction. I want to read the next step because we will see what we need to do with those coordinates. We need to subtract the coordinates of the tail of the direction from that of the head. So I'm going to write the head of the arrow coordinates first, and then the tail of the arrow, the coordinates of the tail next. The coordinates will have x, y, and z values. The coordinates of the head of the blue arrow is given by 0, 0, 1. Why? Because it is one lattice parameter above the origin. And the direction going above is the z direction. The tail, the coordinate of the tail is we need to go one lattice parameter in the y direction, half a lattice parameter in the x direction, and 0 lattice parameters in the z. We're going to do step 2 now and subtract these. So we get minus a half, minus 1, and 1. So we can see that this is basically telling us that as we go from the tail of the arrow to the head of the arrow, we will go back half in the x-axis, we will go backwards on the y-axis, and go in a positive direction in the z-axis. Step 3 now is to clear fractions. We have a half in the x displacement value. If we multiply everything by 2, we will remove that. So we end up with minus 1, it's minus 1. Half times 2 is minus half times 2 is minus 1. Minus 1 times 2 is minus 2. 1 times 2 is 2. So we've got to this step here. The next step is to enclose the numbers in square brackets. If the negative sign is produced, place the bar over that number. So direction C is equivalent to 1 bar, 2 bar, the bar denoting the negative value, 2. These are the Miller indices of the direction C. Let's try some more examples, or calculate some other directions in the same example. So let's have a look at direction B. Let's look at the coordinates of the head in the x, y, and z directions. Direction B, the coordinates of the head is 1, 1, 1. The coordinates of the tail is 0, 0, 0. Subtract 1, 1, 1. Put the numbers in the brackets. If there's a negative, put a bar over that number. We don't need to clear fractions, so we can go directly to writing the Miller indices of direction B as being 1, 1, 1. And this is telling us that the direction is the same direction as we would get had we got one direction in the x-axis, or one lattice parameter in the x-axis, skipped one lattice parameter in the y, and skipped one, or moved along the z-axis with displacement of one lattice parameter. So these are known as Miller indices. Now, there are the values 1, 1, 1. They depend upon the orientation of the coordinate system. And so we can say that groups of directions are actually equivalent. And when we say that this group of directions are directions of a form. When we write directions of a form, we put angled brackets around them. Hopefully now we can understand this micrograph from a PhD thesis. This looks like it must have been taken using a transmission electron microscope. It's of a crystal. Here, the directions in the crystal have been shown to allow us to understand the orientation of the crystal shown in the photograph. This tells us that the arrow pointing this way is equivalent to the 1, 2 bar 1 direction in the crystal. And this direction here is the 1, 1, 1 direction. I talked before about how crystals can be isotropic. That means equal in all directions. Crystals can also display what is known as anisotropy, where the dependence of a physical property of the material depends upon, there is dependence of the physical properties of the material on crystallographic direction. An example of this is the iron alloy used for transformer cores. In a transformer, the energy is transmitted by cycling the magnetization of the iron core. We can make a more efficient transformer if we realize that iron is easier to, if we understand that iron is easier to magnetize in the 110 direction. If we can produce sheets of iron that have an orientation, we can create transformer cores that where the crystal grains are optimally aligned with the applied magnetic field to result in increased efficiency. Here's some, just as we discuss property characteristics of crystal structures, directions can also have characteristics associated with them. One is the repeat distance. This is the distance between lattice points on the line of the direction. The linear density is the number of lattice points per unit length along the direction, and the packing fraction is the fraction of the line along the direction that is covered by atoms. Here is an illustration of the properties of directions in the FCC lattice. If we look at the 110 direction, we can calculate what the repeat distance is, which is the distance between the atoms. And here we can see it's going to be half the size of the diagonal of the unit cell, which is root 2a0 divided by 2. So I have the repeat distance. Another thing would be, just remind myself, so we have the linear density, the number of lattice points per unit length. That is going to be the reciprocal of the repeat distance. And 3, the packing fraction. The packing fraction in the 110 direction is 1, because if I were to draw a line where this represents the 110 direction, here's the origin, we will see the extent of the first atom here, of the second one here, and this third one right there. We can see that there are no gaps in between, and the packing fraction is 100%, or 1. We've talked about crystal directions. The next most important thing to consider are crystal planes. Crystal planes are a set of parallel planes that is an infinite set of planes that can be superimposed upon the structure such that every single lattice point in that structure will fall upon at least one of those planes. Here's some examples of crystal planes for a primitive, for the simple cubic lattice. We can have planes going like so, or we can have a set of planes going diagonally, or a set of planes going from cutting the cube basically along the long, it's kind of hard to express, but we are cutting across this face, and then the cut will pass through the corner that is furthest away from us. And we can have a set of planes like so. How can we identify these planes? Again, we use Miller indices. I'm going to give an example here for the red hatched, which is plane A. And I'm going to apply the step-by-step method for indexing planes in cubic systems. First, we identify the points at which the plane intercepts the x, y, and z axis. If the plane lies directly on the origin, we have to move our origin. Otherwise, this process will not work. So 1, we see that the intercepts on the x. So you see how the red plane is cutting the x-axis at location 1. It's cutting the y-axis at location 1, and it's cutting the z-axis at location 1. The second step is to take the reciprocal of these intercepts. In our case, it's very simple. We just get 1. Clear the fractions, but do not reduce to lowest integers. I'll explain what that means in some other examples. Enclose the resulting number with parentheses. Again, negative numbers are indicated by a bar. So 1, 1, 1. The red plane, plane A, has the Miller indices 1, 1, 1. Let's do some more examples here. Let's look at plane B. First, let's calculate the intercepts. The intercept on the x-axis is 1. The intercept on the y-axis, you see it will cut at y equals 2. And the intercept on the z-axis, well, it never will, because it's parallel to the z-axis, it will never meet it except at infinity. Now we take the reciprocals. One half, and the reciprocal of infinity is 0. Now we clear fractions. Multiply everything by 2. We get 2, 1, 0. So the answer is that plane B has the Miller indices 2, 1, 0. Let's try plane C now. Let's try to calculate the intercepts. Plane C is hatched in grey on this face here. We see that it cuts through the origin. So we cannot use this technique unless we move the origin. Let's move the origin to this point. This now represents the 0, 0, 0 for this analysis. So we have to move origin. The result you get is irrespective of your choice of origin. So it's independent, rather. It's independent of your choice of origin. So here's the 0, 0, 0. It cuts the x-axis at what is now, relative to this origin, minus 1. It cuts the y-axis Oh, actually I made a mistake there. This is the x-axis right here. This is the y-axis. And this is the new z-axis. We see that this plane C never cuts the x-axis, and except at infinity. It cuts the y-axis at -1, and it cuts the z-axis. Well, the plane is parallel to the z-axis, so once again, that's infinity. Let's take the reciprocal. 0, -1, 0. There's no fractions to clear, and so the answer is 0, 1 bar, 0. Let's look at the properties of Miller-Bravais indices. Planes and the negatives are identical. So here we had a negative, but we could also say this is equivalent to 0. If we multiply the whole thing by -1, we get 0, 1, 0. Planes and their multiples are not identical. When we multiply a plane by a scalar, we are actually creating a set of planes that are more finely spaced. A group of planes can be identified as equivalent but have different indices only because of the choice of axes. Such a group are said to be planes of a form. Planes of a form are identified by curly brackets. In cubic systems, the direction with the same indices as the plane is perpendicular to that plane. So in this example, we can see that the plane C, which has Miller indices of 0, 1, 0, is going to be perpendicular to direction 0, 1, 0. And indeed, if we have a look, we can see that plane C is perpendicular to the y direction. And here is the characteristic of planes. We can calculate planar density, the number of atoms per unit area whose centers lie on that plane, and planar fraction is a fraction of the area of the plane that is occupied by atoms. We can use the properties that the Miller indices, which are called HKL, corresponding to the numbers that we get from the reciprocal, but based on the reciprocals of where the plane cuts the x, y, and z axes, respectively. We can use the property that the direction HKL is perpendicular to the plane HKL to determine if a particular direction lies in a plane. If a direction lies in the plane, the angle between them will be 90 degrees. So for instance, if I have a plane and I have a direction, so I'll call this direction A, the Miller indices of the plane will give me a direction HKL. If A is within the plane, this angle here will be 90 degrees. And we can use the property of scalar products to take the scalar product of a direction XYZ and the Miller indices of the plane, we multiply x by h, add that to y times k, and add that to z times l. If that equals 0, that means that the direction xyz lies on the plane HKL. And here we see some examples of the plane here. This is the plane drawn in 2 dimensions and then shown in 3 dimensions of how it relates to the unit cell. So let's index this cell, this set of planes. If we choose, this is our origin, the intercepts on the x, y, and z axis are, this is the x-axis, this is the y, and this is the z. In the x direction it cuts it at 1, in the y direction it cuts it at 1 also, and the z direction it's parallel to the z direction, so it cuts at infinity. We take the reciprocals and we get 1, 1, 0. So this plane is represented by the Miller indices 1, 1, 0. This is what the 1, 1, 0 plane looks like in the FCC structure. This is also the 1, 1, 0 plane, but in the body-centered cubic structure. And we see that it has a different planar density. The planes of crystals are very important. So for instance, the silicon wafers for microelectronics are sliced along directions of a form 100, 110, or 111 planes, depending upon the applications. And here we see a micromechanical structure etched on the surface of a silicon wafer. And see how they have specified the plane upon which the structure has been etched.